next, let's look at example 5 on page 475. Now, to find the zeros of some polynomial. All right, so we have our polynomial, and as we remember from the theorem we just had, the zeros is some kind of a p over q, where p is the last number in the polynomial and q is the first number in the polynomial, and some kind of factor of those two is going to give us a zero. Okay, now that I have said that, then what your book wants you to do is, now we try all the possible factors, and then we're going to do long division. Well, in this case, your book wants you to do synthetic division, which is slightly faster, in order to see which one is a zero of it. Now, to do the synthetic division, I want to point out that there's a zero here. That is, 4 is the coefficient for x cubed, but there is no x squared in the polynomial. That doesn't mean you can ignore it. You have to put 0 here, which stands for the x squared. Now, I haven't covered synthetic division, but the principle is the same with the regular long division. It's when you write out your long division thing, make absolutely sure that you write down the x squared like this. And so like this, see, we have 4x cubed. Don't forget the 0x squared. The same principle applies in the synthetic division. As you can see, there's a 0 there. So then I decided that on the matter of synthetic division, what I'm going to do is, out of respect for the book, okay, even though I think it's a waste of time, I will cover synthetic division at the end of this course, okay, and plus anything else I run along that the book wants you to know that I think is a waste of time, but I guess it's okay to learn it. On the other hand, I will just cover it at the end of this course. So I'll make a note to explain synthetic division if you're interested at the end of this course. And although I wouldn't recommend it, what for? You're lucky to remember this. But anyway, this is the long division format. Either way, just don't forget the 0x squared, okay? It's not written in the polynomial, but it's there, and you cannot let it out. If you ignore it, you will not get the right answer, okay? This thing is going to be off. So is still there, okay? So anyway, so that's how we do this. Now, having said that, I'm not doing this, okay? If you're interested, please do this yourself. And here's what I did. Let me show what I did. I plotted this thing on the Desmos graphics calculator. Okay, let me load it. Now there is that graph, okay? Did I write this one right? Sorry, this is the wrong example. Try. Yeah, I just showed you problem 6. I need 5. Here's 5. Now, I just plotted this thing in the Desmos graphics calculator, and you can type it in. Remember to type in the exponent. You push Shift 6, okay? And then you make the cursor come back down when you're done by clicking it down here or something. Anyway, so once I type this in, which just takes a second, basically, or a few seconds, and as you can see exactly where the roots are. One of them is at 1, and the other one is at 0.5 or something like that. And that is where the roots are. So once I see this graph, then I immediately know that one of the roots is at 1 and the other root is at 1/2. But that's not all I did. The next thing I did is problem 5. Okay, then I typed it in to the Symbol Lab factoring thing. I will write this link below the video. Okay, see where it said I just typed in and used the Symbol Lab factor option and typed in the same equation, and out pops the factor right here. Okay, and that's what we do. So for this section, when you do your homework, so please, what I would like you to do is do this stuff, okay, by hand, like the book says. You do the last coefficient, divide the factors, divide by first coefficient, see which one works, blah blah blah. But once you have done enough of first, I want you to remember how this is done, so you know how to do it and understand how this works. That is, if you had to do it by hand, you could. And once you get past that point and you get to the point and you feel like, I don't want to do another one of these things, okay? I'd rather I'd rather go sweep the floor or something. Now, when you get to that point, which I am there right now, then please pull out the online calculators, which will do all this for you. Okay, and that's what I'm doing. So the summary is do as much by hand as you can make yourself, and the rest of the time let's use the calculators. Okay, they are awesome, right? And so that is all I want to say about example 5. Next, let's go to page 476 and look at the fundamental theorem of algebra, which states that a polynomial that has degree n has n complex roots. Okay, so that means if your polynomial has degree 3, like the one I think we just had, like this one, then it will have 3 roots. Now these 3 roots may be real or not real. Okay, it could be complex, or it can be it can also be repeated. That is, there may be 2 roots that's identical, or 4 roots, 2 of which in 2 pairs. Okay, 2 identical and 2 identical, kind of like having twins. The total number of roots, complex roots, will be the same as the degree. So this one will definitely have 3 roots. And the word complex includes the real numbers. Okay, remember that. That is, the word complex can mean real. Real does not mean complex. Okay, but because real numbers have no imaginary parts, whereas complex numbers can have imaginary numbers, but it doesn't have to. In other words, all real numbers are also complex numbers. So that's why they say complex roots, even though the root might not be complex at all. I mean, in the sense that it might just be real numbers, as we have done most of the time. Now, so let's now that we've said that, let's look at example 6, where we are supposed to find the zeros of this particular polynomial to the degree 3. Now, again, we can do that P over Q trick, where you take the last coefficient, 3, and take its factors, divide by the first coefficient, which is also 3, divide by its factors, mess around, and hope that you're going to find something. Now, so I did not do that. Okay, I just plotted this thing into some calculator. Let me find it. Okay, first, no, wrong. Sorry, let me find it. So anyway, so here's what I did. First, I plotted it out in the graphics calculator, and as you can see, this polynomial has only 1 real root because it's swinging around on top, so it doesn't reach the x-axis, so it has no more roots. Okay, I mean no more real roots. It does have complex roots, of course, because we just had a theorem that said if it has degree 3, it's going to have 3 roots, real or complex. Now, in the meantime, the real root, as you can see, is -3. So you know that much. Okay, you know that this thing has a real root of. So you can do the long division and then factor this thing into something to do with something to do with -3, which means -3, or if -3 is a 0, that means x plus 3 is also is a factor. That's always how it works. That means, see, x plus 3 implies that x equal to -3 is a root. And, well, whatever, or 0, whatever you want to call it. So x plus this thing then equal to x plus 3 times something. Okay, just from looking at the graph. It times what? It times something. It's going to be 3x, because we have to get here. But other than that, this is 3, so it's going to be plus 1. But the rest, I don't know what it is. Okay, but it's something that you cannot factor. Because if you could factor it, then you would have had 2 more real roots. But whatever is here, and we can figure out what it is, but I'm not going to bother. Okay, so what I did is I went on to this is what, problem 6? Where is problem 6? Okay, I went to the factoring calculator, okay, which spit it out right away. Take a look. Okay, wait for this thing to zoom in. All right. See, it factors to x plus 3 and then 3x squared plus 1. Okay, so there's nothing here. No, that's fine. And and that, of course, we can factor. Now, the calculator does not factor anything past the complex numbers as of right now, because we didn't ask it to or something. But we can factor this part ourselves, okay, to get the complex roots out of there. Now to do that, then, so let's do this. So we need to factor this thing, or calculate what is x to make this happen. And the x, bearing in mind the x has to be complex. So 3x squared plus 1 equal to 0, okay? And then we'll solve this thing. Now, there is no real number that this is possible, because any real number you plug in here is going to be bigger than 0, which means when it adds 1, it's bigger than 1. So it will never be 0, okay? So, but complex numbers are a different story. So let's remember how this works. This 3x squared equals to minus 1, right? So then we have, so then 3 square root, take the square root of this whole thing, which we get square root of 3 times x equals to square root of minus 1, which is I, okay? And we had this before. If you don't remember it, that's fine. I'm reminding you right now. Square root of negative 1 means I. So if that is I, then x is actually, in fact, anytime you take a square root, you have a plus or minus symbol here, okay? So both ones are okay. So then we have plus or minus I, and then so then x equal to plus or minus I divided by square root of 3. And these are the other two roots. Now remember that plus or minus sign is a shorthand form to say that, just to mean that I'm saving time from writing this twice. What this actually means is x equal to I over square root of 3, and then x equal to I over x equal to minus I over square root of 3, like that. So this means this, okay? And most of the time, I like to just write it this way because I'm lazy and don't want to write any more than I have to. But otherwise, it has no more meaning than this. And so, but the answer in the book will be slightly different because there's a radical on the bottom, and by mathematical tradition, we don't like radicals on the bottom. We want to move it to the top, and we do it by this trick. We are going to multiply square root of 3. On both bottom and top. This is taught in chapter 1, and if you can't remember or this seems rusty to you, please review this section on radicals until you're good at it again. Looking at an example or two, maybe doing 1 or 2 should do it. Okay, so then so this becomes square root of 3 times square root of 3 is square root of 3 on the bottom, and then oops, sorry, what am I talking about? Square root of 3 times square root of 3 is just 3. Okay, so this becomes just 3 on the bottom, and then the top becomes I times square root of 3. Now, at this point, where you might think, well, this doesn't look that much better than that. Yeah, not than that, right? In fact, you seem to have more stuff down now instead of less. Yeah, but at least we don't have a square root on the bottom, and we don't like square roots on the bottom. Okay, so that would be the root of this equation. So the factoring of this thing, if we are to factor it, originally we had x plus 3. Okay, so let's I'll write it this way. So originally the factoring f of x will become the x plus 3, f of x factors into x plus 3, and then these two roots will be let's see, there's a 3 here. Yeah, then this one will be x minus, there's a x plus I times square root 3 over 3, and then x minus I times square root of 3 over 3. And then, but there is still, there's a 3 here, okay? So the whole thing actually multiplies by 3. Now let me check to see if I should say something else. Actually, the book doesn't even care for us to write this out, so we can ignore that for now. And just remember the roots, the zeros, that is, they're kind of the same thing. The zeros are minus 3 from this part, okay? And then the plus or minus I square root of 3 over 3 from this part. And that's that. So next, let's look at the next page. Okay, next let's go to page 478, where we consider the linear factorization problem, which says that if you have a polynomial, like say this one we just did, it will have as many factors as it has degrees. Okay, so if it has degree 3, you will be able to decompose it into 3 factors, whereas the factors might have real or complex numbers in them. That's basically the same thing as being said it has a polynomial has same number of roots. Okay, well. Anyway, so having said that, let's look at example 7, where we need to find a polynomial, but we are given, my hair is stuck. Let me not worry about it. We are given an example 7 where we're giving, now this time we're giving the zeros, and we need to come up with some polynomial that fit all the zeros. So what are we doing here? We need a 4th degree polynomial with coefficients of -3, 2, and I. And also another condition where f of -2 is 100. All right, how would we do that? First, we pay attention to the I business. If a real polynomial has coefficient I, then it will always has its conjugate, which is -I. Now, in general, if you have any kind of complex number, which means a number that has I in it, okay, or if your number has I in it, such as let's say 2I, okay, or 3 minus 4I, let's say, the conjugate is the one where you change the sign in front of I. That is, the conjugate of 2I is -2I. That you change the sign in front of I. And the conjugate of 3 minus 4I is 3 plus 4I. That is, again, you change the sign in front of I, but you do nothing to the sign in front of the real number. A complex number always have parts in the a real part and imaginary part. Although for in this case, the real part is 0. Okay, or if you consider the number 1 is actually a complex number that's called 1 plus 0i. So every number is in reality a complex number, but real numbers don't have complex parts. And complex numbers or imaginary numbers will have imaginary part and perhaps a real part. That may or may not be 0. So that is the point of the conjugate. The complex conjugate, to repeat, means you change the sign of whatever this thing is in front. If it's positive, you change it to negative. That is, if it's negative, then you change it to positive. So these things are conjugates of each other. Now, having said that, then we're going to do this. The conjugate, what are we doing? That we have a polynomial has zeros of -3, 2, and I. All right. Now there is a rule that says, well, I don't know if it says here somewhere else. Doesn't matter. A polynomial, a normal one with real coefficients, if it has I, it will have -I as a 0. Okay. So this, in other words, this polynomial is. We can write it down. First, it has -3 as a 0, which means x plus 3 is a factor. Okay, it changes the sign of the 0. And then if it has 2 as a factor, then it will be x minus 2. And then it has I as a factor, then it has x minus I. Then it also has, if it has x minus I, it also has a conjugate, which is x plus I as a factor. That is, a -I is also going to be a factor. And then, now this is the factoring of the polynomial, but we don't know what the leading coefficient is, so we will call it A. And then we will find the leading coefficient when we figure out that f of -2 equals to 100. So this whole thing then is equal to f of x. Here's our f of x, okay? And which is fine. And then remember f of what? F of something. -2, right? So f of -2 equal to 0. Equals to 100. As given. Then we're going to plug -2 in, but first we'll multiply this thing out. This is the same as x squared. Okay, let's multiply this. X squared minus I plus I. This is a minus plus situation. So we will apply that same formula where the difference of squared formulas, okay, which equals a plus b times a minus b. We'll do this. You'll remember this at some point, okay, in this course. But anyway, applying the formula, this plus and minus situation, okay, it's just going to be x squared minus I squared. And I squared, what is I squared? Now, remember, I squared, I is the square root of -1, which means another way of saying it is called I squared then equals to -1. Okay, so that is, so we'll put that in here. If I squared is -1, then this is equal to x squared plus 1. So that's what that is. So this entire polynomial is x plus 3, x minus 2, and x squared plus 1. But it multiplies by some a here. Now, what is a? We'll figure out by plugging x as -2 in here, here, and here, and then figure out what that is. So what's, so let me do that. Yeah, so -2. So what is, when x is -2, plug it in here, that f of -2, I'll write it down here, it will be equal to a times -2 plus 3 is 1, -2 minus 2 is -4, and then down here, -2 squared is 4 plus 1 is 5, and that equals to 100, because that was given. And then, so then a would be equal to, a times -20 is 100, so a is negative something, 5, right? Something like that. So I don't want to think too hard, so let's check. Yep, a is -5 times this stuff. And then the next thing your book wants you to do is multiply this thing out, which, well, do I want to do that? Maybe. All right, so let's multiply this thing out, okay? It sounds like a lot of grunt work, but okay. So let's multiply this part out first. What is x plus 3 times x minus 2? Doing that, that would be, I'll write it down here, f of x equal to, do this. X plus 3 times x minus 2 is x, just this part, okay? We're just doing this part. X plus 3 times x minus 2, that's x squared. Okay, now plus 3x and then minus 2x, that's plus x, right? Okay, and then plus 3 minus 2 is minus 6. So that part isn't so hard, x squared plus 1. The rest of it is far more annoying, right? Plus I ran out of space. I will do it over here. Okay, let me erase a little bit. Oh, what? I forgot to write down a here. Okay, don't forget the a, because a is in front of the polynomial. So let's write down -5 here to show we didn't forget it. But we will not pay attention to it for now, and let's just multiply this stuff out. We'll do this one time, okay? And then we'll never do it again, because there's a calculator that would let you crank this out very quickly, which is what I normally do when I have to do this in calculus or something, which doesn't happen very often, okay? I hardly ever have to do this. So anyway, let's multiply this thing out. So just to make sure that you can do it. Now remember, to multiply any amount of stuff with another bunch of stuff, these are these things are called a term, and then this is a term. They are each like a guy, okay? These are guys or girls, doesn't matter. And then these are, they are all from the same group. And these are guys from a different group. So that's a guy, x squared, and that's another guy. So each guy here has to shake hands with a guy from the other group one time, okay? And no more. Just each one will shake hands with that guy one time. So we're going to do that. First, we'll start with x squared. X squared will shake hands with each of these two guys over there. And okay, so that gives us, I'll write it down over here, f of x equal to x squared times x squared is x to the power 4th. X squared times 1, that's x squared. Okay, first guy done. Next, second guy stands up to shake hands. Plus x times x squared, that's plus x to the power 3. Plus x times 1 is plus x. Lastly, the last guy stand up to shake hands. Minus 6 times x squared is minus 6x squared. I'll write it over here. Minus 6x squared, because it looks similar to that guy. And then minus 6 plus 1 is minus 6. So writing it next to that guy didn't do me a whole lot of good. Well, whatever. So that's about it. So we'll write it down in descending order of the power. Okay. So that would be oh, I forgot the -5 again. I'll write it here. -5 times all the stuff. So continuing, this is -5 x to the power 4th. Okay. That is -5x squared. So -6 plus 1, that's -5. And sorry, I already said that we're gonna write it in descending order. Let's not bother. I already wrote it. I don't want to bother. That's x3 plus x minus 6. Okay, that is and then there's a -5 in front. Is that right? And let me check. -5 x4 plus x3 minus 5x squared plus x minus 6, and then we multiply it out, and I don't want to do that anymore. Okay, so we'll call this done. And but you can go ahead and multiply it out, and that gives you the final conclusion of example 7, which is not that exciting, but you do need to know how to do this. That is, how do you multiply a pack of guys with another pack? Doesn't matter how it could be 3 in here, could be 500, doesn't make any difference. You do it the same way. Each guy will take turns to stand up and shake hands with every other guy on the other one at a time. Okay, so that is the principle you go by, and then if you don't mess up and do the math wrong, then you will get the right answer in time. So that is example 7. So next, let's go to the next page after I erase the board. Next, let's go to page 479, where we consider René Descartes' rule of signs. And now in the middle of the box, let's read this thing. Okay, according to the Descartes' rule of signs, then let's say we have a polynomial, right? Then the number of positive real zeros is equal to the number of sign changes. That is, let's look at the example right on top of this box. Okay, we have f of x equal to something. Okay, let's look at that example. This is on the same page. We have f of x equal to this stuff, and how many times did the sign change? In this case, there happened to be only one change. It changed once. So what does that mean? It means, according to this statement, Descartes' statement here, the number of positive real zeros is equal to the number of sign changes or less than it by an even number. Well, it's not possible to be less than 1 by even number to be in the matter of counting zeros. Therefore, this thing has one positive real zero just by counting signs. Isn't that neat? So you know that René Descartes was sitting there on a Friday night and doesn't have a date, so he sat around, stared at this stuff, and discovered all these lovely things. Okay. And so that's what this sentence means, which means as we count the change of signs, then we can have an idea of how many, positive zeros we have. Now, what about the negative zeros? The same principle, or should I say a similar principle applies. For negative zeros, then you first have to plug in the negative x, which means you flip all the odd signs. That is, the even numbers stay the same, right? We're starting from here. So if you stick in the negative x in there, then the even number will stay the same because the negative signs cancel out. The odd coefficients are all changed. So that plus will become negative for x to the power 3 and so on. So then you get a different situation where now, how many change of signs do we have? Suddenly now we have 3 changes of signs. And the principle is still the same. The number of negative real zeros is equal to the number of sign changes, in this case 3, or is less than that by an even integer. So it can be, it could be 3, I guess, because this thing started out with the power 4. And we already said that it has 1 positive real zero, so it could possibly has 3 negative real zeros, or maybe 1 negative real zero and 2 imaginary complex zeros. Anyway, so yeah. So that is the René Descartes' rules of signs, which is a very cute Okay, and so I suggest you do it once just to get the feel for it. But in practice, I never do it because I just plot it out in the graphics calculator and let's stare at this thing. But it's still a cool rule to have. René Descartes is probably the greatest mathematician before Euler, in my opinion. He is the one who argued, who made the famous statement, "I think, therefore I am," and also that he also argued that it is not possible for any kind of machine that we make to somehow develop self-awareness, that your machine, like Commander Data in Star Trek and on Star Trek, the Next Generation, it's just you cannot create anything that has that kind of that becomes a person, or never mind person, become a dog, and which has happiness and sadness and all that. You can at most pretend that it does. You kind of like how AI nowadays, okay? But the AI pretends it's a person and it has happiness and sadness and all that, but it really doesn't. It's just faking it. So that's René Descartes' philosophy. Which I totally agree with. Okay, I believe it is not possible for humans to come up with some kind of machine that becomes Commander Data, which is not something I'm happy about. I would rather believe that Commander Data is possible. He's my favorite character, but I have to admit that to myself that it's just not going to happen. But anyway, so that's the whole bit. Now, as far as the signs go, please do this. Okay, it is quite straightforward. So I'm not even gonna go over it. You just follow the rules, and then as shown in example 8, and that will tell you how many real zeros, positive or negative real zeros you got on your polynomial. And then after you've done this once, it's kind of like vacuuming. The vacuumer is a fantastic invention, but that doesn't really make me want to vacuum my room any more than ever. Okay, so then but it is a cool rule. So please do it like once or twice in your homework, and then we'll move on. And then so next, let's look at example 9. Example 9 is a word problem, which is so on the next page 480. So let's look at that and read this thing. Okay, it says that if you glance through this thing, eventually you get what we're getting is that there is some cake. Okay, in the shape of a box, average cake, no special shape. And the cake has to be a volume of 351 cubic inches. So V equals to 351. All right, but that's not all. The cake, the length has to be 4 inches longer than the width. So if the width is W, let's just call it W, then the length has to be W plus 4. W plus 4, I'll write it down for now. Okay, it says, right? Yeah. And the height is 1/3 of the width, and the height has to be 1/3 W. And then the question is, what does W has to be in order to come up with this exact volume for your cake? So the way to solve this problem then, of course, is length times width times height equals to 351, which I will write it down right here. Okay, actually, I'm not going to write it down. This is, well, imagine this in your head. That means this is a polynomial of the variable, the highest degree 3. And then you do something, and so that you get that. Now to solve this, please plot it into the, to solve a W, please plot this thing into the, into either the graphics calculator or the factoring calculator. Either one will work, because if the answer, any root that's complex, you don't want it, right? I mean, why would you get a complex width for your cake anyway? So the roots has to be real, and if it's negative, you don't want it either, because why do you have a negative width for your cake? So the root has to be a reasonable number, and then what do they want? What should the dimension of the cake pan be? Okay, now so that once you figure out the width, then you figure out the length. This is the length, and figure out the the thickness, and that is the dimension of, that is the answer. So your answer has to come up with 3 points after you figure out W. Now I'm going to have you do this by typing this simple this times that equal to that into any calculator, and it will spit out the answer at you right away, and that will be the answer. Now having said that, let's look at the question a little more, okay, that I want to make a few comments. The actual problem says, a new bakery offered decorated multi-tiered cakes for display and cutting at quinceañera and wedding celebrations, as well as sheet cakes for children's birthday parties and other special occasions to serve most of the guests. Now that entire sentence, if you were to read it, you need to forget it immediately from your memory. Why? Because these are called extraneous information in a math problem, and it's there to throw you off, okay? We don't care that this is a bakery, and we don't care about quinceañeras, and we don't care about celebrations or children's birthday parties. Not because those things are unimportant, but because that is irrelevant to our current problem at hand. And we need to focus, whatever the heck are we doing here? We're doing this. This is it, okay? So all these other information, you need to toss it out as soon as you read it. For now, that is. And then the next and the next information, first, the volume has to be 351. The shape of the cake is a rectangular solid. That's important, because if it's a circle, then we're talking about something different. And then all the other requirements are important. And then so once you get the answer, then you're good. Then you can go back and worry about the bakery, the cakes, the quinceañera, the weddings, children's parties, anything else you want to worry about. Okay, nothing wrong with that. But when you are doing this kind of a problem, you need to block out all the other information so that you can focus on what matters, to what is relevant to the math problem at hand, so that you can get the right answer. So that is an important skill that I want to mention sometimes. Other times I just ignore that stuff and don't even talk about it. So then let's turn the page and see how your book did this. And as you can see, the book wants you to try these solutions, okay? Based on what we have learned, let's see, why is my... let me wait for my camera to focus. All right, see the middle of the page right here where it says it wants you to try, never mind the negative answers, because we only care about positive roots, right? And being that this is a real world application, and the book wants you to try to divide by 1, 3, 9, 13, 27, 39, 81, etc. Okay, I'm done talking. It's but that is, which is one reason I tell you, let's not do that. I mean, what are you, a saint? Let's just not. That is way too painful, okay? If you were to do that, you probably throw this book away and never look at my videos again, because it sounds so, But please don't do that unless you really want to. And it won't stop you from continuing this course. Then, feel free to do that. There's nothing wrong with doing it. And so, and I also want to mention that the solution of this problem at the very last sentence says the sheet cake pan should have dimensions 13 inch by 9 inch by 3 inches. That is completely impractical. That happens to be the standard cake pan size, 13 by 9. I know, because I do quite a bit of cooking. But I'm telling you, you do not bake a cake by ordering the exact size of a cake pan. Okay, cake pans come in standard sizes. You will buy, if you need the cake to be a specific volume, then you need to buy a bigger pan and then cut it when you're done, right? Like, why would you order a special cake pan for a specific size? That's just weird. And of course, I also must mention that does it ever happen that a bakery wants a cake to be 351 cubic inches? I would venture to say no, that this does not ever happen. Okay, never. This doesn't happen. It's just this problem is. I've never done that, and I'm a mathematician, so I do not believe for a second that any bakery would care about this kind of thing. But anyway, having said that, however, let's beat this problem by plugging it into the graphics calculator, because we do have that now. Even the book knows that. So why are we working so hard? that's gonna that's really gonna wear you out, except for mathematical saints who don't mind doing this stuff. You know, like Rene Descartes. But anyway, by the way, Descartes never got married, I was told. Anyway, so then we have come to the end of this section. For homework, which is on, well, first please do all the examples. Again, for homework or example, please do as much of it by hand as you can make yourself, and the rest of the time just use a calculator. Okay, and then let's get through this stuff and not have to think about it too much, because we'll have far more exciting stuff later. Okay, and there's far more exciting stuff in calculus than just doing grunt work. So so homework on page 482, yes. Please do problems 11, 17, 25, 31, 37, 45, 53, 59, 65, 67, 73, and 79. And when you do use the calculator and you look at it, and then you should notice a few things, like where the roots are and how you would have done it by hand if you had the patience for it, that sort of thing. And that's good enough. There's really not much going on here. All right, so please go do your homework, and when you're done, I might do a problem or two. Now that you're done with the homework, I want to do problem 67. Okay, so problem 67 is says that we have some real root, okay, which is -1, which happens double. This happened 2 times. Okay, I'll write down 2 times. Is that good? Well, whatever. So -1 show up 2 times is a double root, and 1, which shows up 1 time. And then another information is f of 2 equal to 4. That will help us determine what the leading coefficient is. So, because this only tells us what the factoring are, but it can be multiplied by anything. So then the solution then is x plus 1 2 times. So we'll write it down again, or just write squared, either way. And then times x minus 1, and then times some kind of a. Okay, so next we need f of 2 equal to 4, so to figure out what a is. So this is f of x. So if f of 2 equal to 4, so we'll write down 2, okay, and then let's plug in 2 here, so that be a times 2 plus 1 is 3, squared is 9, and then 2 minus 1 is just 1. So that equals to 4, which means a equals to 4 divided by 9. Okay, and then you plug that in here, and that should be the right answer, except that the book probably wants us to multiply this thing out, which is okay, I guess. All right, so let's do that. Maybe that's not. Do I want to do that? Nah, I really don't want to. Why don't you do that by hand yourself? Okay, this part becomes, I'll do this part, which is x squared plus 2x plus 1. Okay, that's this part. This is probably something that you want to memorize. That is, x plus 1 squared is automatically not x plus 1 squared, but something like a plus b squared. This is because we use this so much. Memorizing it would be make doing the math a little bit faster. A squared plus 2ab plus b squared. Now this situation happens quite often in homework sections. Then, well, if you say, well, I don't really want to bother memorizing it, that's fine. You will memorize it eventually because you'll be doing so much of it, right? But or you can just memorizing it now and get it over with. So anyway, so this thing times x minus 1. And that is actually not that bad. Maybe I should do that. So let's do this. Okay, since I'm standing on this side, we'll start with this group. This guy will stand up and multiply with each guy on the other side, which will be x. First one, okay, is x times x squared, which is x to the power 3. Second guy plus 2x to the power 2. Third guy plus x. That's the first. Okay, second guy stands up. The second guy is -1. Okay, that sign stays with him. So -1 times x squared is minus x squared. I'm writing it down here so the things are lined up and might be easier for me later. minus 1 times 2x is minus 2x. And finally, minus 1 times plus 1 is minus 1. Now let's, so that round up to be f of x equal to, don't forget the a. A is 4 over 9. Okay, we'll write it down here. And then copy the steps down with doing some of the math. So x3, that would be plus x squared, right? X squared. And then minus x, minus x, and then minus x, all right? And then minus 1. That should be the right answer. So let me check the back of your book. It says, yep, that is correct. So that is how you do these things. This happened to be a somewhat simpler, less painful problem. But it could be a lot more painful, depends. But whether it's painful or not, you go about it the same way, systematically, one at a time. So that is 67. Okay, next let's do problem 73. All right, and then the volume is some weird number. Yeah, I knew it. 73, problem is problem 73. We have the length is 1 inch more than the width. Okay, so let's say width is here. Okay, length is 1 inch more, so w plus 1. And then the length is 1 inch more than the width. The width is 1 inch more than the height. Okay, so the height is w minus 1. Because it just said the width is 1 inch more than the height. Okay, so read this thing carefully, and well, anyway, so the volume equals to whatever. So these three things multiplied together is equal to 86 point whatever, 0.625 inches to 5. All right, so then to figure out what the width is, then we multiply this stuff out. This becomes w squared minus 1. Okay, that's the plus and minus situation, which is equal to a squared minus b squared equals a plus b plus a minus b times the w here, which, okay, times the w. And then we minus the 86 point whatever to 5. And that equals to 0. Okay, and then let's type this thing into some graphics calculator to figure out where it hits where its zeros are, and then call it the answer. And yeah, and I don't want to do that, so I'm going to skip that. I just want to tell you about the problem. Yeah, so next let's look at something. So this problem 79. We are considering a right circular cylinder. That is this thing. Okay. Now, here's our cylinder. You can draw one of these things. And it's like, what is like? Maybe, well, anything that's in that shape. The radius and height differ by 2 meters. The height is greater. So here's a radius. We'll call it r. And the height is greater than the radius by 2. So the height will be r plus 2. Okay, so this is r plus 2. And down here, the radius is from the center of the circle to the side is just r. All right, so far so good. And then the volume is whatever it is. All right, and then so what are we doing here? We're trying to find the radius. All right, so the area of a circle is pi r squared. Now please memorize that. Okay, pi r squared is the area of a circle. So and the volume of a cylinder is base area times height. And that's true with all things that's the same all the way up. Okay, it's base area times height. It doesn't matter what the base area look like. It can be a rectangle, a square, a triangle, or a circle, or some other odd shape. As long as it's consistent all the way through, that is, there's no dent in there, it's consistent all the way through up, then perpendicularly, then it has the base, the volume is always base area times height. So then in this case, the area of the base is pi r squared. So we'll write down pi r squared, which is the area of the base, times height, which is at r plus 2. And that is going to be equal to, what is it equal to? Where is it? Oh yeah, the 28 point something. There's 28 times and 1/8 pi. Yeah, the 0.125 is 1/8. Okay, but anyway, am I right? Yeah, 28 and the 1/8 pi. So once we've done that, then Then you solve this equation by putting this on this side, so everything goes as, equals to 0, like this. We'll cancel out the pi here, because there's a pi on each side of the multiplication. So you can cancel that out. So that and multiply this out, it becomes r squared plus r cubed plus 2r squared minus 28 and an eighth, and that equals to 0. And you don't even have to multiply it out, I don't think. I think the calculators can even handle this. But you should probably put it on this side so that we know what you're factoring, okay? Then type this thing into the calculator and you'll spit something out and pick the answer that makes sense. You know, nothing, we don't want any negative numbers or any numbers that sounds odd. That is, the whole thing multiplied together to be about 28 is the volume. So R should be, I don't know, less than 28. I don't think it's, maybe 5 or so. Yeah, 4 or 5, something like that. Doesn't matter. It should be something reasonable. Okay? It better not be 1 million, for example. Anyway, so that's that. And that's the end of this section.